Hi there! Welcome to a new episode of the Synth project where we are going to build a synth together. Holiday season took a toll on me because I didn't have much time to work on my projects, but, although late, I was still able to run the tests that I planned on a new chip I discovered, the SSI 2130, which I introduced to you in the last episode of this series. I'm really excited for this chip actually. Based on my findings, I couldn't have found anything better to work with, although I found a couple of minimal issues that can be resolved very easily with a few extra components, and so nothing to worry about. Let me share with you all the goodies I found inside this small but powerful component. Hi there! I am Carlo Carrano, and this is Electronics Engineering Made Easy. Here is the SSI 2130 on its red breakout board. The breakout board sits in the same space as a regular 32-pin DIP socket. Pins from 1 to 16 lay on the left side, while pins from 17 to 32 lay on the other side. Before doing anything else, I reassembled the voltage reference generator on this big breadboard. It uses all the components I used for the previous version of the small breadboard. I will now power up the circuit, and so we can tune the voltage reference and have it ready to be connected to the rest of the VCO circuit. This breadboard will be powered up with the same kind of power supply that is going to be on the actual synth shelf. So we are going to have a plus 12 volts, a minus 12 volts, a plus 5 volts, and of course the ground. The LEDs that I have turned on the breadboard are the ones to monitor the presence of the power supply on all three rails. Now I am going to connect the negative probe of my multimeter to ground, and the positive probe will go instead on the output of the voltage reference unit, and so we can tune it. Now we can turn on the multimeter, which is set to read the DC voltage, and it currently shows a reading of 5.7 volts. And so we need to act on the tuning trim pot to adjust the voltage to exactly 2.5 volts, which is the value required by the SSI 2130. So far we have 4 volts. Now we are at 3.7, 3.5, 3.2, 2.9, so now we need to slow down to avoid passing the point of 2.5 volts. Okay, this seems to be close enough. It's just 1 millivolt away from our desired value. Let's see if we can do even better than this. Yeah, we actually need to have a precision of about plus minus 15 millivolts, but I'm trying to have it as precise as possible to avoid that the thermal drift makes us going outside of the requested range. Okay, yes, this seems to be fine now. So it's time now to build the rest of the circuit around the SSI 2130. Here is the schematic of what I am about to build. The circuit is mostly the same as the one presented on page 5 of the datasheet. There are just a few changes to make it feasible. For example, you can see here that there are a bunch of resistors in series. In the original schematic there was only one resistor, but of a value that does really not exist in the market. And so I had to use a number of resistors in series to obtain a value as close as possible to the one actually required. It is important to notice that all resistors in the schematic are supposed to have a 1% tolerance, and so they will be very close to their nominal value. But putting a number of resistors in series to obtain a value that is not commercially available reduces a bit the overall tolerance of the component. So I will have to measure a few resistors from my stash to find those that are more precise, and so I will be able to be very close to the required value. This is something that you will have to be prepared to do. It will happen again in the future with other modules besides the VCO and with other components, not just resistors. Having components of a precise value makes possible to obtain the necessary precision on the notes emitted by the synth, and will guarantee also that thermal drift will not cause any bad effects. So back to the schematic, the SSI 2130 is in the right center of it. The paths for the external connections are lined up at both the far left and the far right of the picture. And the rest of the schematic is basically a reproduction of the original schematic in the datasheet, where the pads are connected to the central IC with the appropriate components, when needed of course, or otherwise are directly connected. You can see, for example, how the triangular wave output is directly connected to pin 1, while the 3 exponential control inputs are connected to the pin 7 through appropriate resistors. Capacitor C7, along with R19 and R20, take the generated triangular wave and inject it into the sine shaper input, so we can obtain a nice sine wave made available on J16. The capacitor that provides the time base is C8, which needs to be one that does not drift much from its value with the temperature. There are special capacitors called C0G or NP0, but we can replace this particular one with a polystyrene capacitor, or wood quality of course, that behaves very well in such circuits. And in fact, the datasheet itself suggests doing so. There are also a couple of variable resistors in the VCO circuit. This one on the top right, RP2, is actually a linear potentiometer that can be used to modify the duty cycle of the pulse wave emitted by the circuit. RP3 instead is a multi-turn trim pot that needs to be tuned to perfectly shape the curve used for the exponential converter. There is in fact a whole procedure to do so, more on that later. Switch S1 is used to change the output of pin 29 between sawtooth and ramp. The sound of the two is practically the same, at least to my ear, but sometimes you need to use one or the other depending on what you want to achieve with further audio processing. The 5 inputs J7 through J11 are for controlling the VCAs in front of the mixer inputs provided by the SSI 2130. The first 3 mixer channels are already used for the triangular wave, the sawtooth wave, and the pulse wave, but the last 2 are left available for other uses and are accessible through J2 and J3. You can use these 2 auxiliary channels to input either the other waves produced by the VCO or totally different external signals. J17 on the right side is used to input a sync signal, which will force the VCO to drop the current period of the signal being generated and to start a new period. This kind of synchronization can be used to align the beginning of the wave period of the VCO to another external wave, or to force the VCO to produce a specific frequency. We will see that better later in the video when watching the circuit in action. And finally, the last thing I wanted to point out in this schematic is the voltage reference generator built around D1 and U2. If you are interested in understanding how this part works, I suggest you to revisit the previous episode of this series, for which the link is coming up now on the upper right on the screen. And now let's go back to the actual circuit, which I have already assembled on this breadboard. At the center there is the new IC. This area above it is the voltage reference circuit that we already seen. And this is the rest of the circuit. As you can see, there are several components, mostly resistors and a few capacitors. This support holds the PWM potentiometer and the switch to select ramp and sawtooth waves. Let me now explain what is all this stuff. You can see that I put a number of labels all around, and these are there to make it easy to identify the various test points and functions of the circuit. These 3 here are the inputs for the voltages that control the frequency of the VCO. These 5 are instead the voltage inputs to control the VCA that are in front of the mixer channels. These all around here make essentially the circuit that I described in the schematic, which is basically the same provided with the datasheet of the SSI 2130, with the changes I already described. We have a bunch of outputs, and here is the square wave, the pulse output, for which we can adjust the duty cycle from this potentiometer. Then we have this other output, which can be either a ramp or a sawtooth, depending on the position of this switch. On this position is going to be a ramp, and on this other position is going to be a sawtooth. And then we have the sine wave output, which is available because I already connected the components on this other side to have the triangular wave feed the sine shaper. This one is the capacitor that generates the timing base. And this one is the mixer output. This is the 3 input that will be used for tuning the exponential converter. And these are 2 auxiliary inputs on the mixer. Note that of the 5 waves that we can generate, only 3 go directly to the mixer. The other 2 channels of the mixer are free to be accessed from the outside and are marked as AUX1 and AUX2. I'm not going to use this potentiometer, so I'm going to remove it from the breadboard. This potentiometer is connected on one end to the ground and to the other end to the plus 12 volts of the power supply. This provides a variable voltage control that we can use to test the various control inputs of the SSI 2130. Right now, the potentiometer is connected to a VCA, but let me put it here to one of the exponential control inputs so I can show you later how this control behaves. So let's turn on the circuit and let's see how it works. First, I am going to connect the oscilloscope probe to ground over here and to the triangular wave output so we can see this wave on the oscilloscope. I'm also going to move this potentiometer to change the control voltage of the exponential input to see how a change in voltage causes the frequency to change. Right now, the potentiometer is all the way to the left, which means that it is connecting the exponential input directly to the ground. Here is the visualization of the output of the oscilloscope. You can see that right now there is basically nothing, and in fact the oscilloscope is registering a frequency of 1 Hz only. Now I am going to increase the voltage of the exponential input by moving the potentiometer to the right. You can see now how the oscilloscope is registering an increase of the frequency and the shape of the wave is changing accordingly. Actually, now I can adjust the oscilloscope controls so I can show you how the triangular wave looks like at this moment. Here you can see that it is perfectly triangular shape that develops all above the ground level, and so it is not symmetrical with respect to ground. Its amplitude at the peak is 2.5 volts, which, by the way, is exactly the value of the voltage reference applied to the system. And in fact, that is what the voltage reference is all about. It is the one that is used to regulate the charge and discharge of the timing capacitor, which happens through a constant current generator and therefore creates such shape. You can see how we can go higher and higher with the frequency just by increasing the control voltage and the exponential input. Here we are at 67 Hz. Let me change the scale of the oscilloscope now so we can have a better view of the wave's shape. And now I am going up so we can experience how wide is the frequency range of the VCO. So here we are at basically 3 kHz now. Going from 1 Hz to 3 kHz, we practically have an excursion of 12 octaves. Not bad at all, right? But I can go even further actually. And that would happen if I would start applying a voltage also to the other exponential inputs. See, I have here 3 inputs, and I'm only using one. I can actually add as many inputs as I want just by adding more resistors. Putting voltages to all such inputs, I would increase the current pulled at pin 7 of the SSI 2130, and thus I would increase the frequency even further. Technically, according to the specs, I could go up in the neighbors of about 60 kHz. Let's try now some other experiment. Let's remove the oscilloscope probe from here and put it on the square wave output. Yeah, here it is. You can see that it is a pretty nice square wave, actually, very well shaped. And now I'm gonna move the probe to the pulse output, here. Right now the duty cycle is set to about 50%, and so the wave still resembles a square wave. But now look what happened when I move the potentiometer associated with the pulse duty cycle, which is this one here. As I move it in one direction and the other, you will see how the duty cycle changes. Let's go with one side first. In this case it looks like the duty cycle is increasing as the upper side of the wave gets bigger than the lower side. But now if I continue to move the potentiometer in the same direction, the duty cycle keeps increasing up to the point it becomes almost 1 or 100%. And actually if I move the potentiometer all the way in that direction, at some point the wave entirely disappears and it is replaced by a high voltage. It is like the pulse is so narrow it is not visible anymore. And then moving back the potentiometer, the duty cycle starts decreasing and becomes smaller and smaller. It seems the control is very effective and works as promised by the datasheet. Now I am going to move the probe to the ramp output. There it is. Now if I move this switch, the ramp becomes a sawtooth. And you can see how we can go back and forth, and the shape of the wave changes accordingly and instantly, without any glitch. Let's now take a look at the sine wave. Whoa, look how beautiful it is. It is very well shaped and it is also symmetrical with respect to ground. That's a very nice feature. Another thing we can take a look at is the mixer output. Here I have now connected the oscilloscope probe to that output, but as expected we don't see anything coming out of it. It is expected because we are not driving with any voltage the control inputs of the VCAs of the mixer. As soon as we put a voltage to one of the VCA control inputs, we should start seeing something. So to make this work, I will have to rearrange a little the external part of this circuit. First I am going to remove this wire that connects the potentiometer to the exponential input, and I am going to connect it to the control input of the first channel of the mixer. To be able to see a signal, however, I still need to put a voltage on the exponential input, and to do so I will use a voltage coming out of this power supply. This way I will be able also to know exactly what is the voltage I am applying to the exponential input. So, this is the cable that comes out of the power supply, and I have connected the ground of the circuit to the ground of the power supply. The actual voltage can be now extracted through this white wire, which I am connecting to one of the exponential inputs. And now let's take a look at the oscilloscope. Here it seems to be a triangular wave, which is correct because the first channel of the mixer is actually internally connected to the output of the triangular wave. However, note that the shape of the signal is now symmetrical with respect to ground. If I now change the voltage on the power supply, you see that the frequency of the signal changes as well. And that was expected, of course, since we said that the power supply now controls the frequency of the VCO. If I change the voltage of the control input of the mixer by moving the potentiometer, it is the amplitude of the VCO signal that changes, and that because we are controlling the VCA in front of the mixer input. Let's now take a look at the second channel of the mixer, which I am enabling by moving the white wire from the first input to the second. This one should be the channel to which the sawtooth is connected, and in fact the oscilloscope confirms that. And we can still control the amplitude of the wave and also switch from the ramp to the sawtooth just by using the corresponding switch. Now let's move the control voltage from the second input of the mixer to the third. This one should give us the pulse signal, which is the one internally connected to channel 3 of the mixer. And it is, as we can see from the change in the duty cycle, that I am causing by moving the PWM potentiometer, which is the duty cycle potentiometer. Note also that all the waves we have seen so far at the mixer output have a peak-to-peak voltage of 2 volts, which is a little lower than the 2.5 volts we would expect. This is actually something I need to fix with an external amplifier, since we want that all the signal sources emit the same level of signal, which I decided to be plus-minus 2.5 volts. And since we are working on a mixer, let's see what happens when we mix together two signals. So, this is the pulse signal, and now I am adding on top of it the triangular signal just by providing a control voltage to the corresponding mixer control input. Look, now they are mixed together and I can change the shape by just changing the duty cycle of the pulse wave. Very cool. Think of all the possibilities for creating all kinds of shapes. Another thing I would like to show you is how to use the sync input of the VCO. The hard sync in particular, which is the one that we want to use. To input the sync signal, I am going to use my function generator, which is currently set to provide a square wave at 100 Hz and 5 volts of amplitude. To do that, I am going to put the ground connector from the function generator to the circuit ground, and the signal connector to the hard sync input, which is connected to the corresponding pin of the SSI between 130 through a capacitor and a resistor. Look what happened at the triangular wave that was being captured by the oscilloscope. And look at the frequency of the current signal. So this is happening because every time the sync signal goes down, the current period of the triangular wave is interrupted and restarted again. Because that happens much faster than the VCO frequency, the shape of the triangular wave is cut just at the beginning of each cycle, and the effect is this ramp wave. Increasing the frequency of the sync signal, the frequency of the VCO output increases of the same amount, because now the cycle of the triangular wave is interrupted even earlier, and in fact we see that the level of the output signal is even lower than before. To confirm that that is what is happening, let's considerably decrease the frequency now. So you can see now that the triangular wave is interrupted much later, and it has the time to almost complete each cycle. And here is the point where the sync is happening. Note the frequency of the VCO output, which, although we haven't changed the control voltage, has decreased to 40 Hz from the 200 Hz it was before. So here is the effect of the sync. With it, we can force the VCO to interrupt earlier the current cycle of the wave and start immediately the next. See, if I change the sync frequency, you can see that I can change the moment when the synchronization happened, and the wave changes a little bit in shape. Now, before closing it, I wanted to do one last thing. I wanted to attach the VCO to my lab audio amplifier, and so you can hear the actual sounds being generated by the VCO. So let me remove some useless stuff. I'm gonna remove the oscilloscope right now, which we don't need. I'm gonna remove the connection with the power supply, providing the control voltage, and instead I will provide again the control voltage with my potentiometer right here. Okay, so now I can control the frequency with my potentiometer. This one is the input of the amplifier. I'm gonna connect the ground to its place here, and then I'm gonna put the sine wave for now, and then maybe I will show you also the other waves to see the difference. That's the minimum. So look, I'm increasing now. This is a frequency very low right now. I'm increasing. Let me show you now the same effect with a triangular wave. This is a triangular wave instead. Let's increase the frequency. You see, this is a little sharper than the sine wave, of course. And now let me move to the square wave. This should be even sharper. Low frequency. Increasing. And finally, let's take a look at the pulse. And so I can show you the effect of changing duty cycle. So look at that, I'm changing duty cycle now. And this is it. And now let's go to the last thing I would like you to see today, the procedure to tune the exponential curve of the VCO input voltage. The tuning procedure is explained in the datasheet of the SSI 2130, but there are a few steps that are not so clear and therefore merit some extra explanation. The best way to do that is to go over the whole procedure and following it step by step. Since we will need to know exactly the input voltage, I put back in the circuit this power supply to provide the control voltage. First step is to inject a control voltage of exactly 1 volt. So let's adjust the power supply to provide such a value. The oscilloscope is connected to the triangular output, and I am going to measure the frequency of the signal under these conditions. And the reading is about 2 Hz. In actuality, we should not use the oscilloscope for these readings, because we have to make precise measurements of the frequency. A frequency counter would work much better to do that, as it would allow to measure even the decimals of the frequency values. For now, let's continue this way, since this is just a demo on how to do it, but when we will build the actual VCO, we will use a real frequency counter for this step and the next ones, where a frequency read is required. Let's write down the frequency at 1 volt, which we will call FA. And now let's set the input voltage to 5 volts. And the frequency is now 31 Hz, which we will write down as FB. The procedure now requires to calculate the logarithms of these two numbers. We need to use logarithms because the input is actually exponential, and using the logs we will make the numbers look like linear, and we will be able to calculate the slope of the exponential curve very easily. When I calculated the logs for the first time, it took a while for me to realize that the procedure was asking to do that in base 2, not in base 10, and not even the natural logs. The base 2 is required because we need to calculate a slope expressed in octaves, and we know that 1 octave is a distance from one note and the next that is 2 times higher in frequency. That's the 2. Problem is, now, that I do not have a calculator that is able to compute logs in base 2, but fortunately I found a calculator like that online. To do that yourself, open your favorite browser and look for a log base 2 calculator. This is the first one that I found, and it works perfectly for what I need. I'm going to put the URL of this calculator on the video description in case you would like to use the same calculator. To use it, just put the number in the first line marked as X and read the results in the next line, which will appear automatically without doing anything else. For the first log, we need to calculate the log base 2 of 2, which is obviously 1, but I will still do the calculation to show you how this works. So I'm going to put a 2 over here, and the result comes out immediately and of course is a 1. Let's write down this information too, which I am calling A. And now we calculate the B value, which is the log base 2 of 31. Let's zoom in a bit so you will be able to see better the numbers. Typing in 31 and the log is 4.954, which I'm going to write down here. Now we need to calculate the difference B minus A, which we call dy, and the result is of course 3.954. We also have to calculate a dx, which is the difference of voltages between the two readings. And since we used 5 volts and 1 volts, the difference of course is 4. Now we need to calculate the parameter t, which according to the datasheet is the intercept of the exponential curve, which is given by a equals dy over dx. And so it is 1 minus 3954 divided by 4. Let's get the calculator to find the result. So this is going to be 1 minus dy, which is 3.954, divided by 4. And the result is 0.0115, which we write down to. Now we need to calculate the target frequency, which is the actual frequency that we should have found with a 5 volts input. To do so, we need to calculate the value of t, which is I plus 5 times the slope we require to have, which is 1 volts per octave. And so t is I plus 5 times 1, or just I plus 5. And therefore t is 5.0115. This t is basically already the target frequency, but it is expressed as a base 2 log. To get the actual frequency, we need to calculate 2 to the power of t, which is... well, we need a scientific calculator for this one, so let's switch to it. Okay, now we can do 2 to the power of 5.0115, and this gives us 32.5. And this one is the frequency that we should have. But the frequency we got on the oscilloscope is 31 Hz, so we need to act on the tuning trim pot to obtain the correct frequency. And of course, the oscilloscope is not capable of capturing the frequency decimals, so I am not going to adjust the trim pot now. However, once we build the actual VCO, we will use a real frequency counter to make the measurements, and therefore we will be able to do the tuning appropriately. So, to summarize what we have seen, we can say that the SSI 2130 is up to our expectations and even more. I don't think there is any doubt at this point that this will be our choice to build around it, the VCO module. There are only 3 things that I will have to take care in the design. First, I will add some circuitry to make symmetrical those outputs that are not, and I will also adjust the amplitude to have it at 2.5 volts peak to peak. Second, I will have to protect some of the input pins of the IC to prevent high voltages from burning the chip. And third, I will need to make a slight adjustment to the output signal of the mixer, which I want to be exactly 2.5 volts peak to peak when the control voltage of the VCAs is at its maximum. With those 3 changes, the schematic will be ready for prime time, and we will be able to actually make a good VCO module with plenty of extra features. We will go through all of that in the next episode of the series. In the meantime, I'll see you in my next video, and as usual, happy experiments!